Thanks a lot again. So this is just for the taping, right? So there are no speakers. So I should use...
There is a speaker.
Oh, there are speakers. Okay.
So we hear you much better like this.
I see. And if I speak like that, is it still hearable? Okay. So thanks a lot for giving me an opportunity to be here at such a nice place. Not that hot, actually. I came from north, and it's still reasonable. So what I'm going to speak about is the Planar Ising model. And well, when I thought about the introduction, I planned to say that there are tons of papers written on the Ising model, and then I started calculating. You know, it might be true. So if you assume that an average paper is about 100 grams, then it might be true that actually there are tons of papers on the Ising model. So obviously, but I didn't check. So obviously, okay, what I'm going to do is just an introduction to the subject, and moreover, this is going to be an introduction from perspective that I and my co-authors use. So, okay, there are various people in the room, and for some of them, what I'm going to speak about is a triviality. I apologize, but still I discussed with Leo, and it sounds that there are people who doesn't have any ground in the Ising model, so I'm going to start with really basic things, and then we'll see where we are. So the plan for today is basically to discuss the combinatorics of the model, so and the formalisms people use to study it. So if you are interested and you want to have a reference, a few years ago we wrote a sort of a survey paper with David Simazoni and Adrian Castle. So it is called Revisiting the Combinatorics of the Ising Model. So this is a reference on combinatorics. And basically, I'm going to follow the notation of that paper. So for today, this is the combinatorics. Then, okay, depending on the speed we go, with which we go, please feel free to ask questions. So if you just don't understand something, raise your hand and we'll discuss. Then we will discuss, well, other things like maybe explicit computations or theorems on scaling limits and so on and so forth. So, but that's for today. So that's today. And as I already said, okay, we start with just very basics and what is the definition of the Ising model. So you start with a graph, with a finite graph, and what I'm going to do is a planar model. So for me, it's going to be important. So you start with a planar graph. By chance, it happened that I have one. So here is a planar graph. And okay, when I say planar, I always think that it is already embedded so that all the edges are straight lines. So maybe here they're not that straight. Okay. And then what you do, you consider configurations of plus minus signs assigned to the faces of this graph. So attention, this is not the standard notation. A standard thing is to consider just a general graph and to assign plus minuses to vertices of it. So what I did, I already used the planar duality. So for me, okay, now I think about configurations of spins. Labeled by, is it visible, by the way? If I write like that, should I use larger script? No, that's fine. So, okay, I should use larger. Okay, so what you do, you assign plus minus variables to faces of your graph, and attention, as I said, this is non-standard. Usually to vertices, not to faces. And then, okay, I should specify a probability measure on such configurations. And the probability measure on such configurations works as follows. For every edge you fix a constant, which is called just a real number. In my case, it's going to be positive. So it's called ferromagnetic Ising model. And then you say, okay, the probability of a concrete configuration, here is the main definition, is proportional to what? So, again, you just sum over all edges. So this is a kind of an area integral. So you sum over all edges such terms. So again, what is what? So constants j, they're just fixed once forever. Spins, those are plus minus ones. And beta is yet another parameter which is called inverse temperature. So that's the standard setup of statistical mechanics if you ever heard about statistical mechanics. Inverse temperature. So here, okay, a way to think about it. So if two nearby spins are aligned, if they have the same, if the variables have the same value, then this probability is bigger, right? The integer is, okay, smaller. It should be 2 minus signs here. Okay, the probability of such configuration is bigger. So the most likable configuration is just all pluses or all minuses. Yeah, J's are, in my case, are positive too. It is called ferromagnetic model. So in principle, this is not necessarily. And for the combinatorics part, okay, there is no that big deal with the sign of J. Later on, J is going to be positive. Okay, so is the definition clear? Modulo the fact that we have a lot of parameters pre-assigned to such a thing. Okay? So just a picture like that. So what is marked on the picture is all the edges that separate pluses from minuses. Okay, each such an edge decreases the probability of configuration. Then what are typical questions one studies in statistical mechanics? Instead of thinking of a single graph, what people are interested in is just consider various limits. So either when such a graph is, say, a subgraph of a lattice, and you move and you increase it, enlarge it more and more so that you have a model in the full space. Or maybe setups when such a graph approximates a concrete domain in the plane, something like that. So in principle, we are not going to work with a fixed graph, but for a while it is just given. Okay. Now what I'm going to do, so there is an important quantity which is called the partition function. And in terms of the probability measure, it is hidden in this sign proportional to. So what I said, okay, it's proportional to this quantity. Okay, sorry. The prefactor is actually of importance. So let me discuss this partition function of the model. So I'm going to discuss two ways to see it. And yeah, I just understood that I didn't make an important comment. So in such a setup, what I made, I marked plus everywhere outside. Okay, so if you are just thinking combinatorially that I'm given a planar graph, then there is a prescribed face, which is the outer face. And what I do, I just say, okay, let me fix the sign here to be plus. Okay? Anyway, the model is fully symmetric under the simultaneous change of all the sigmas of flipping the sign. So I can break the symmetry by assigning plus to the outermost face. Okay. So let me discuss the partition function. And what's the partition function? This is by definition just the sum over all configurations. Oops. Let it be calligraphic Z. Sum over all configurations of that quantities. I'm going to rewrite it in a slightly different way. And right now, this is quite a triviality. So what I'm going to do, I want just to, to collect factors. OK, just take a look. What I take, I do a product over all edges of what? OK, each there is sum, right? Each term of the sum contributes either exponential beta g or exponential minus beta g. So I just factor out all the exponentials plus beta g. So this is the product of these things multiplied by an object. Okay, multiplied by an object which I'm going to discuss in more detail. So what is that? This is the sum over all even subgraphs of G of the product over edges of this subgraph of some variables. And what is this variable xe? This variable xe, by definition, is exponential minus 2 beta g. So what happened? Look at this picture. Configurations of pluses and minuses, they are in one-to-one correspondence with these collections of yellow or green edges. Okay? So to be able to recover a configuration, the only condition is that this collection of yellow edges, they're called domain walls because they separate pluses and minuses, is an even subgraph of G. Right? So basically, the sum is over the same set, right? And this weight, okay, this is exactly, it contributes 1 when there is no edge, and contributes exponential minus 2 beta j if there was an edge in C. Okay. So that's just a combinatorial way, another combinatorial way to rewrite the partition function. Equivalently, I could say that the probability to see such a configuration is just proportional to this product of variables x. Okay? So somehow, in this description, you should understand x as a price to draw this edge. Okay? The more edges you are drawing, the less probability is. Okay? Are there any questions on that? Okay. If no, then let us go further. And now what I'm going to do is to present another technique for the Ising model, which is not limited to the planar case, and which is called the high temperature expansion of the model. So another viewpoint. So let us now change the perspective and let us consider the model defined on vertices of the graph. I mentioned that this is a more classical setup. So consider a model, as a model on vertices. And again, just to define the model, I should specify what the interaction constants are, and probably I should also say what the inverse temperature is. Okay, so the parameters are inverse temperatures, beta star, and interaction constants, and GE star. Okay. So what I'm doing, okay, I want to think about what is the total partition function of the model. And a remark, I do not specify any condition now for vertices at the boundary. So I just think, okay, let them be pluses and minuses freely. So it is called free boundary conditions. Okay, let us do a short computation. So yet another way to compute the partition function of the model. It's called high temperature expansion. for some historical reasons. In the Ising model, there's actually not an expansion, so the name expansion comes from some asymptotics, but in the Ising model, it's the identity, an identity. So, okay. What do I do? Okay, let me think about this. This exponential. Some G star VV plane. I put stars everywhere just to emphasize, just not to mix the notation, just to emphasize that I'm now working on the dual graph. Okay? And let me think about this. There is the sum in front, thanks. There is a sum in front over all possible configurations, indeed. Thanks. Thanks a lot. And let me think about each of these terms in the sum as a product over edges, but now I interpret it as follows. So this is a product of hyperbolic cosine of B G star plus sigma sigma hyperbolic sine. What I did, I simply said, okay, this product of two spins, it might be either +1 or -1, so there are just two values, and I should check that this matches when the product is +1 and when the product is -1. Okay, and now what I want to do, I want simply to develop this product. Okay, so this is a product over all edges, and I'm developing it. What I want to say is the following. So first, there is a prefactor, which is just the product over all edges of hyperbolic cosines. So this is a triviality. Now I have one here and hyperbolic tangent there. Okay. And then what remains is sum over all spins, over all spin configurations, product over all edges of this. Okay, let me rewrite it. Of this one plus hyperbolic tangent. VV plane. Now, an element of such a when I develop all the brackets, elements of this huge sum, they are indexed by subgraphs of G, right? I can say, for instance, that my subgraph just indicates all the terms where I choose the second term in this bracket. Okay? So when developing this sum, when developing this product, sorry, what I have is a sum over all possible subgraphs. And then what happens when I sum over all possible spin configurations? When I sum over all possible spin configurations, actually only those graphs where each sigma participates in an even power survive. Right? So typical element is just the product of hyperbolic tangents, sigma 1 to some power, sigma 2 to some power, sigma 3 to some power, etc. And all the powers must be even so as to survive when I sum over plus minuses. So what I want to do here is a conclusion, and okay, if you have a question, just ask in a second. So what I have is the following conclusion. This is the product over all edges of this hyperbolic cosines. 2 to number of vertices multiplied by exactly the same factor as on the left, multiplied by the sum over all even subgraphs, product xe over the edges of this graph, where now xe has a different value, a priori different value. which is a hyperbolic tangent of beta star G star. So again, you don't see what I write, or you don't understand? The red part is unreadable. Okay. And if I try to write the same in white, this is hyperbolic tangent beta star G star E. So this is this value. So in general, white is better than red, you say. It was just a matter of writing. Okay. So yet again, what happened? Just think about a typical term in this expansion and what happens with this term when I sum over all plus minuses. So generically, it just disappears because there is a variable in an odd power. But if all the powers are even, then, okay, when you sum over all configurations, there is this additional factor 2 to the number of vertices, which pops up. Okay, so from now on, I just want to keep it as it is and introduce a different notation, which is still Z, but not calligraphic anymore. So just notation. ZG is just sum over all even subgraphs. X of C and XC is by definition just the product over all edges. So this is the notation, and okay, just keep in mind that if I want to compute a partition function of the model, then basically there are 2 ways to get to this quantity. One of the ways is okay, on the left, other is on the right, another is on the right. Okay. An even subgraph is by definition just a subgraph such that all the vertices have even degrees. That the degree of each vertex is even. Okay? Other questions? Okay. And now, well, of course, certainly the partition function itself is maybe not the quantity you are interested in being a probabilist. So you would better been interested in some probabilities, etc. But nevertheless, what I want to start is just to discuss how to compute, how one can attack computation of the partition function of the model, basically of this quantity. Okay, how to compute Z. That's the question to discuss. Well, how many of you know anything about Daimer model, the Daimer model? Just please raise hands if you, okay, just 50-50 roughly. Okay, good. So then I'll indicate what is the Daimer model and okay, how one computes the partition function of the Daimer model. So first, let me do the following combinatorial trick. It is on the sheets with notation. If you just turn the page, there are many, many graphs drawn on the sheets you have. So, okay, if you don't have paper, please raise your hand. So let me do the following transformation of my graph. So for every vertex, if I had, say, vertex of degree 4 here, what I do, I replace it, I construct a new graph, an augmented graph, which has actually quite more vertices. Like that. So this is a local construction. And in that notation, this graph is called GF due to Fisher, who used, well, more or less, well, a version of this construction in 70s. And now what I do, I say that instead of considering edge configurations on the original graph, I consider what is called dimer configurations on the new graph in the following way. Imagine, for instance, that here I had 2 yellow edges. Then what I do on my new graph, I just keep these 2. So I say, okay, these 2 edges are taken. And I do not take these 2. So I say, no, those are not. And the problem, so what is the dimer model? The dimer model is the following thing. You are given a graph, not necessarily planar in principle, but okay, in my case, planar. And you want to study all the perfect matchings of this graph. So you want to study all collections, I mean, or random maybe, or just collections of edges such that they cover all the vertices exactly once. So what happens on this picture? So I said, okay, this edge is taken, this edge is taken, this is not, this is not. Then how should I proceed so that every vertex in this small city is taken exactly once? Well, I definitely know that this edge is not there, this is not there, etc. So just a trivial consideration shows that what I need to do, I need to cover by something is wrong, right? Yeah, because here there was a point. So there are 2 edges. This is a hexagon, not a pentagon, actually. Just take a look on the sheet you have. So a simple consideration shows that basically what I need to do is to fill this hexagon by edges. Okay, so the correspondence is actually 1 configuration here to 2 to the degree of the vertex there. So given whatever even number of yellow edges on the left, I have 2 to the degree ways to fill edges on the right so that every vertex is covered exactly once. And altogether, this corresponds to, okay, 1, 2, sorry, just two, one option here, two there, and altogether this corresponds to 2 to the number of vertices choices. So, okay, on the left, I have even subgraphs. On the right, I have dimer configurations. Subgraphs. Actually, dimer configurations of the F. Yep. I keep, so here let me introduce the notation like long edges, those edges who are obtained from the edges of G, and short edges, there are some additional ones. And then what I do, I keep all the long edges that are in these configurations. I do not keep those who are not taken in this configuration. And then I ask myself how many choices, I mean, how many ways to fill the small city I have. And the answer is that for every vertex, I have just 2 choices. The recipe is that I should cover these 2 to, okay, this hexagon in this example. So I can do it either like this 3 edges or the way around. So this is 1 to 2 locally at every vertex and 1 to 2 to the number of vertices globally. Okay? And in particular, well, I should of course also keep track of the weights of this graph. So what I do, I say I keep a weight of this edge to be x, and here I put weights 1 everywhere. And then this 1 to 2 to something correspondence is weight preserving. And basically the question of computing Z is now reduced to the question of computing the partition function of the dimer model on this auxiliary graph. Okay. that's not. Okay. This is equivalent to partition function of the dimer model. And that's a very, very classical combinatorial problem, which is called the Castellane Theorem. So there is a very nice way to compute such a function. And this is basically the subject of the problem number 1 of this TAE session. Okay, there is a Castellane Theorem. Okay, what should I do? So the Castellane theorem tells that there is a clever way of signing the adjacency matrix of a given planar graph, which leads to the partition function of the dimer model. Okay, yet again, what is the partition function of the dimer model? I should sum over all possible dimer configurations on my graph, and each configuration is weighted according to this axis in my example. So what is the Castellane theorem? There is a way to introduce rent edges of, say, GF, but this GF, it might be whatever planar graph. So just whatever planar graph. Such that the partition function of the dimer model on this graph equals to a Pfaffian. If you know what the Pfaffian is, if you don't know, just take a look here. This is signed adjacency matrix. Signed and weighted adjacency matrix of my graph. Okay, question might arise. Here I speak about orientations. Here I speak about signed adjacency matrix. What is the link? So this A is antisymmetric. And basically, okay, given an edge from V to V prime, you say that A VV prime is plus its weight and A V prime V is minus X V V prime, provided that this edge is oriented from V to V prime. Okay? So basically, we start with a non-oriented graph, then we introduce orientations, and then the adjacency matrix is naturally antisymmetric. Okay, there is a concept of a Pfaffian, and if you never heard about what is a Pfaffian of an antisymmetric matrix, it's fine if you think just about, so first it should be absolute value, and it might be either plus or minus, and it's fine if you just think about the square root of the determinant. So, well, I suppose that like half of you already know this statement, and another half never heard about it. So that's exactly the subject of problem number 1. That's somehow a miraculous fact. It happens that the partition function of the dimer model on a planar graph can be effectively computed. So that's the message of the subject. It's just a question of computing determinants, which is a priori, of course, is not at all trivial. Okay. So far, so good. Any question?
This combinatorial bijection we had, that's 1 to 2, not 1 to 2 to 3.
This is 1 to 2 locally, meaning that at every vertex I have a choice. And this is why here is the product of choices. Okay? Good. Now, when we... Yeah, well, that's... I don't quite understand the question. So what do you mean by in general? Yeah. That's a very good question. So, okay, this, yeah. So right now, look, I'm just thinking about finding graphs. I don't consider any limit. So if you are, say, interested in an infinite volume limit, then, say, some periodic models, then, okay, what you might imagine is first a reduction to the torus case, that you consider a model on bigger and bigger tori. Then this bijection should be slightly massaged, because there is a question of periodicity and antiperiodicity, what happens there. But effectively, what you get is phi-fins of adjacency matrix on a torus. And those matrices can be diagonalized because they commute with shifts, with rotations here and there. You can actually write down what the eigenvectors and eigenvalues are. And if you wish, this is a computation. In particular, this is a way to see the phase transition. I'm going to see the phase transition other way around, but okay. Okay, now what do I want to do? I want to make a few remarks. So remarks on this computation. The very first remark is that, again, you can massage. Yep. Yeah, it becomes, instead of a single phi-fin, a sum over all spin structures on the surface. And so this is a sum of phi-fins, which is 2 to 2g, which contains 2 to 2g terms. It is indexed by spin structures, and the coefficients, there are plus minuses in front. They are invariants of this thing. Just consult the paper reference to which I raised. There is a section on how general surfaces there. So yeah, I'm going to stay somehow down to earth in this class. Okay. So what are the remarks? Let me. So there are two, and the first is that one can massage this correspondence further. So one can consider other graphs instead of GF. So instead of GFs, one can consider, well, okay, one can consider other graphs. And there are at least two examples which are a bit useful to have in mind. I'm not going into details of these correspondences, but still I want to keep in the noosphere two other examples of such graphs. So two others are both non-planar, and you have them, I hope, in front of you there. So the first, we call it GK due to Castellane. This is a non-planar one, and locally it looks like that. And yet another one, we call it GC, and locally it looks like that. So this is more a remark to address to those of you who know what the dimer is. So here the Castellane theorem deals with counting dimers on planar graphs. And there is such a magic of finding an orientation. So that's really a magic. In general, it is not available. So just given a graph, and I don't know, non-planar one, if you want to find an orientation of its edges so that this is true, you basically fail. The necessary and sufficient condition is that there are no K33 minors, if I remember correctly. So K5 is okay, but K33 is not. Okay, nevertheless, there is always a way to find an orientation here, an orientation of edges, so that what you count is a signed dimer configuration. So signed dimer configurations. The sign is as follows. Each time you have a crossing, like that, you put -1 per crossing. So here I counted all the configurations with the same sign. And what I'm now saying is that if my graph is non-planar and for some reason I assume such a convention that each time I have two crossing dimers I put -1 in front, then it is always possible to find a generalization of the Castellane orientation. So, okay, for those who know what dimers are, these graphs, they're also useful, and this is an exercise to construct, which is not listed in the problem set, to construct combinatorial correspondences with such graphs. Okay. Now, remark number 2 is the following. Okay, it was already a question raised. What are effective ways to compute these Pfaffians in this or that setup? Keeping this away, let me ask a more naive one. So imagine that, say, being a probabilist, I'm not a pure probabilist, but okay, being a probabilist, I'm interested just in the probability that a concrete edge is contained in a configuration, that the concrete edge is yellow. Probability that edge is a configuration. How should I compute it? If I think about dimers, then basically what should I do? I should count all the configurations with this edge and divide the partition function of such configurations by the total partition function. But assuming that a given edge is in my dimers configuration is exactly the same as just deleting this edge out of my graph and covering everything that remains. Okay? When I delete my edge and count dimers on the remaining graph, this is exactly the same problem. What I get is a Pfaffian of a matrix which just has two smaller rows and two out columns and two out rows. Okay? So basically, this is just the probability that my edge is taken into a dimer configuration. It's just the ratio of a minor, of a Pfaffian of a minor of this matrix over the Pfaffian itself. And this is clearly just the entry of the inverse matrix. Okay? This is just the entry of the inverse matrix, entry indexed by what? So that's a question. Again, you have this in front of you. So what is a convenient notation for vertices of my new augmented graph? So there are vertices of this type, which is in one-to-one correspondence with oriented edges of my original graph. Okay? Every such vertex is just, I can think about it as an oriented edge of the original graph. And this is the same edge oriented differently. And vertices of such a type, and these vertices, they are just in one-to-one correspondence with what is called corners of the original graph. So each time I have a vertex, then, okay, there are corners here. Okay, just a notation that you can consult each time, when you feel lost. I apologize, there is a lot of, the notation is really heavy. There are a lot of things. Yeah. Yep, and it should be, of course, absolute value. Thanks a lot. Yeah, that's an absolute value. Or you should keep track of. So E and E bar, so here I ask what is the probability of an edge of the original graph to be in the configuration. Okay? What I'm saying is that to every edge of my original graph, there are two vertices of GF associated. And I think about them as oriented edges of my original graph. This is associated with E, and the other is associated with E bar. Okay? Yep, that's it. So this is E bar. And this is like E unoriented, or whatever. Or you can think that, okay, that's the same for E and E bar. So message. In whatever setup, say, when I think about big graphs, when I think that this is really a big system, and I want to answer a question, what is the probability to see an edge right here? What I should do, I should analyze the inverse matrix. Okay? That's the message. Moreover, if I want to think about what is the probability to see a collection, a given collection of edges, what is the probability to see simultaneously this, say that, and this in my collection, that's exactly the same reasoning. So what I should do, I should remove all these vertices from my graph. I should count the number of dimer coverings of the remaining part and divide. So instead of a single entry, what I will have is just pfeffens of small submatrices of my matrix A. So more generally, okay, these edges of my configuration, they actually form a Pfeiffer process with this kernel A minus 1. Pfeiffer process. In particular, if I want to study whatever correlation function of edges in this or that scaling limit, this inverse to A is exactly the thing I must analyze. Questions? Well, if no, then let me pose a question. So of course, there's edges. That's a very nice thing. But maybe this is not what we're interested in the model itself. Because the model originally is about spins. And OK, so this is some information about spins, but not satisfiable. I mean, what should I do if I want to compute, if I want to attack the question of what is the expectation of a spin here and there? OK, but what about spins themselves? And before moving to here, let me change the notation slightly. So here I said that there is a matrix A which comes from the Castellane Theorem, which is fairly general. And each time when I'm given a graph, say GF, or a graph GK, or a graph GC, I will denote the corresponding matrix like K hat, C hat, F hat, and hat somehow indicates that this is an antisymmetric matrix, that there is a kind of an antisymmetry there. I'm not going into the formalism of Grassmann variables, but okay, if you're familiar with the formalism of Grassmann variables, you can introduce it right now just by saying that, okay, I'm given an antisymmetric matrix, and this is a Hamiltonian in Grassmann variables. Okay, so what should I do if I want to think about spins themselves? And here is an answer. And the answer is, again, like high school level. So imagine that I want to study the correlation between this and that. So I want to know whether they are of the same sign, whether these two signs are the same or they're different. Well, okay, high school recipe is what I should do. I should draw a path connecting these two faces in question, like a path like that, and to count how many yellow edges I cross along the way. So if this number is odd, those two guys are different. If this number is even, those two guys are the same. Okay, that's triviality. But look, so this Castellane theorem is purely algebraic statement and doesn't know anything about signs of x's. So this is just a question like one polynomial in x variables coincides with another polynomial in x variables. And this counting of the parity of the edges is actually the same as to say that all x variables assigned to edges crossing this path, I must change signs of them. So what I do, I change, invert, flip the signs, reverse the signs, change the signs of xe along this path. Of the path, connecting given spins. Yep, I choose some path for a while, and I just do this procedure. And then the trivial observation I can do is that the expectation of, say, CU1, etc., CUM, since I assumed that the spin of the outer face is fixed once forever, I can relax the condition of parity here. So in particular, I can think even about a single spin. Then this path simply connects it to the boundary. Okay? So when I think about this expectation, what I should do, I should take the ratio of two pfeffens again. And okay, let me work, say, with the matrix K. Maybe at the beginning of the TA session, I say a word why this K, how is it related with yet another approach to Dyson model. But right now, this K is simply its signed adjacency matrix of the graph GK with this magical correspondence of signs such that it indeed counts dimers with plus minus per cross. And what do I mean by this index? And by this index, I mean exactly the procedure indicated in orange on the right blackboard. So this is exactly that. So I take my matrix, I flip the signs somewhere, and okay, what I need to do, I need to take the ratio. By the way, Okay, yeah, like that. And even there is no need to put an absolute value here, so an absolute value boils down to plus minus here and plus minus there, and they cancel each other. Okay, unfortunately, this doesn't answer a question on how to attack this quantity in big graphs. Because, well, all right, these matrices, they're quite different, and the procedure, well, okay, this is something. Maybe it can it is boiled down to some sum along a path, but still, if the graph is huge, if the spins are very far from each other, okay, that's a complicated story. Nevertheless, there is a remark. So there is a quantity which is much easier to understand comparing to this ratio itself. And this quantity should be thought of as a special derivative of this ratio. So imagine, try to think about what happens when I move one of the points one step. So imagine that what happens, think about what happens when, say, U1 is replaced by neighbor U1P. You want to compare two such quantities. Okay, trivially, you can write that the ratio of these two expectations is just the ratio of two such pfeffens. But now you can say that, but look, these two matrices, they're pretty much the same. So what I should do, I should prolongate this path one step. Right, so what I should do, I should change just the sign of x on one more edge. So these two matrices, so effectively, this one is really small rank perturbation of that one. Okay? Like rank 1 or rank 2, depending on the notation. So, okay, basically to analyze this ratio, the only thing you should do, you should have a control of the inverse matrix. Okay, so provided you have a control of k minus 1 u1 um, provided you have a good control of entries of this matrix, you can control these ratios. And then, okay, hopefully you might say something. Okay. So yet again, the moral is that when thinking about spin correlations and when trying to prove things about them, it might be more useful to think about their increments, okay, or logarithmic increments, rather than about correlations themselves. So again, how this matrix is defined. So basically, each time, I mean, in each of these formalisms, each time when an edge, say, in this formalism with f, each time when an edge crosses my orange path, I simply flip the sign of x. So I replace x by minus x. Well, just if there are two, it's just a path linking them. If there are many, then okay, they're linked pairwise.
Okay, and it doesn't matter if you have to
Yeah, that's a byproduct because it counts the same thing. Okay? This is a very good question. Yeah, this is a very good question because yeah, let us discuss it. Because here it looks like I made an arbitrary choice, but this is not the case. Effectively. So the answers, they're independent of this choice. And moreover, it should be, so that's exactly the subject I'm going to pass to. So it should be an invariant way to see this picture. Somehow, instead of choosing paths, choosing cuts, you might think about double covers, which branch here and there. It's just a more invariant way of describing the things, and that's somehow exactly the topic I'm going to post. So, okay. This was the story how people doing combinatorics think about the Ising model. So some formalism which reduces the model to the Dymers-Counts problem. And now what I'm going to discuss is a formalism that actually physicists use and which is in fact an extension of all this Dymers story. This is called the Kadanoff-Seva formalism. If you can check, it would be great. So, okay, this Dymers story, somehow this is a good entrance point for those, especially for those who know about Dymers. And this is something more complicated for probabilists, but yet again, much more usual for physicists. So I'm going to introduce yet another set of definitions. And what is important is that it happens that they lead exactly to the same correlation functions as if you worked with Dymers. Okay, so what is the set of definitions? So yet another bunch of notation. Sorry for that. Okay, let us keep spins alone for a while. And let us think about vertices. So let us think about a given collection of vertices. I'm going to introduce what is called disorder, correlation of disorder variables. So just define. And right now, I'm cheating. So I'm defining the whole quantity on the left, not emphasizing at the moment what is the random variable. So just think about this as a single sign. And later on, I mean, in a second, I'm going to specify. I'm going to say that this may be viewed as a random variable. Okay, and how this thing is defined? It's a bunch of some notation. Okay, this quantity ZG is just the partition function of the model. This is sum over all even graphs of XC. So the question is, what is this Z superindex VVV? And by definition, I say this is the sum, again, over all X of C over some set of graphs. And this set of graphs, those are even graphs except at the given collection of vertices. So, okay, here are like 4 vertices V1, etc. V4. And what I do, I sum over all subgraphs of G of that kind. So all the vertices are even except these. Right now, you can think about this as just a pure combinatorial construction. Okay? So is there any question about this quantity? Just how it is defined? Yep. Yep. Well, that's quite relevant. So, okay, you can, so first, what I did under the name high temperature expansion, this is like a marginal of the random current. What you do, you just keep only the parity of n. So random current is an assignment of n's, and what you do, you just keep the parity and sum over all towers. Then this is a marginal of the random current representation, and that's exactly what I'm going to discuss. That here, this is related here. That's a very good question. So again? What is in yellow? In yellow, yeah, that's like an artistic picture of this collection of edges. That the degree is odd. Yeah. Oh, yeah. Except, yeah, not only except, but okay, those things, those vertices, they do have odd degrees. Yeah, thanks. We do condition on degrees of them. Yep. That's exactly, yeah, that's a very good question. So I decided to start with the definition, and that's exactly what I'm going to discuss. I mean, how to view this in terms of domain walls and how to view this in terms of the high temperature expansion. This is going to be exactly the same. So that's here. That's the topic for the last 20 minutes, just to see the duality yet again on this language. Okay, so now at least we have right-hand side well defined. I promised you to explain that this thing can be viewed as a random variable. So this is what I'm going to do now. So on the right, it was a formal combinatorial expansion. And the first comment is that to view this expression as a random variable, what you can do the following. You say, okay, let me fix, similarly to this story, let me fix a collection of paths linking my v1, vn pairwise. So let gamma v is a subset of G. Be paths linking v1, vn pairwise. And let me consider the random variable, which is just the product over all edges crossing this. The paths of exponentials, okay, of x e to sigma u sigma. So what do I do? That's exactly the same. So by definition, this is exponential minus 2 beta ga sigma u sigma. So what effectively do I do? I say, okay, here was v1, here was v2, and here there was a pair of faces interacting across this path. And what I now say, I say, okay, if this was plus plus and it contributed 1 in the original configuration, now I say let it contribute x. Other way around, if sigma sigma was minus 1, so that what am I saying? This is, am I saying nonsense? Yep. And what I'm saying, if sigma sigma was -1, so this contributed x, then I multiply it by x minus 1 back, so it now contributes 1. So in other way around, what I do, I change the rules of drawing an edge in this picture. So what I do like, so in this correspondence between spins and collections of contours, I do the XOR operation with this gamma v. Yeah, that's a single variable. So let me emphasize that. Each particular mu is not a random variable, but each product of an even number of those I can interpret as a random variable if I wish, just by doing this arbitrary choice. In particular, the answers does not depend on the collections of paths, but the random variable. So if I want a probabilistic interpretation, then this random variable does depend on the collection of paths. But the distribution, yep. Well, remember still that each particular mu is not a random variable. Yeah, then the distribution, and if V1, if the endpoints are fixed, then the distribution is independent of the choice of gamma. Yep. Okay, now this is an interpretation in terms of domain walls, and what I now want to do is basically to answer your question on how it is related with random currents, but not mentioning random currents, just with high temperature expansion. Okay. Remember when I spoke about this ZG, there were two ways to view this partition function. The one is the partition function of the model on faces of my graph, and another one, actually even more general, is the partition function of the model on the vertices of my graph. So, okay, what happens in the dual picture? In the dual graph picture, what you say is the following. Just let me consider the expectation of sigma v1 star, etc., sigma vn star. So now this is a different model. I put stars everywhere just to emphasize that I'm on a dual graph now. And let me do the same trick. So what is the same trick? I say, okay, this is again a product. Okay, overall, this is a sum over all configurations, product over all edges, hyperbolic cosine that plus sigma v prime hyperbolic sine multiplied by sigma v1, etc., sigma vn. Okay, and what was the trick? The trick was to develop this product, just open all the brackets, and then to take sum over sigmas. Now, what do you see? You see that the relevant terms are not indexed by even subgraphs. No, and rather they're indexed by subgraphs from this collection. Those which have all the degrees even except at v1, vm. Because what we want is that the monomial in sigmas that comes from this product multiplied by sigma v1, sigma vn has all even degrees. Okay, so what I want to, to say is that just similarly as above, as at the very beginning, what you get is exactly this product. Oh, this ratio, sorry. So, is there any question about this development? No. Okay, now in the exercises, you have a generalization of this statement, which is a problem number, I don't know, something, problem number 2. Generalization. One can actually think about mixed correlations of spins and disorders. One can think about product of many mu's disorders by many spins. Where if you want a probabilistic interpretation, each time you say, okay, I fix a collection of paths, so on and so forth. Okay. 2 messages more in the exercises. The first message is that this quantity has a combinatorial expansion similar to these things. You should count signs carefully. You should count what are the graphs you are summing over, but okay, there is an expansion. And second message is that there is a self-duality. That this identity, that the product of mu's has the same distribution as the product of sigma stars, can be generalized to such things. Just take a look on the exercise sheet. Yeah, that's a statement. So this is the exact statement. So I start with mu v sigma u, and in the dual picture I have sigma star v because now spins are assigned to vertices, and I can, in a similar fashion, introduce mu's, and okay, just expanding combinatorially, you get this identity. So somehow the message is that there is a duality in the Ising model, which is called Kramers-Vanier duality. And disorders, they're exactly dual objects to spins under such a duality. Okay. Still, we have 10 minutes for more pain. So, okay. Let me continue commenting on these quantities because that's of huge importance. Comments on these quantities. I want to develop this explanation with switching the sign of the interaction of u and w along these paths slightly further. Okay. I already mentioned the idea that instead of fixing paths in all constructions of such a time, there is a more invariant way of passing. So again, what are so here mu's are labeled by vertices, not. Nope, those are not plus and minus 1 labeled by vertices. If you want an interpretation of a random variable as a random variable, this is a random variable. This is something complicated. This is a huge, huge product. And spins, they are still just plus minus ones. There is no single mu. Yeah, that's what I discussed with Leo. Yeah. Yet again, let me try to say it loudly. There is no single mu. So mu is not a random variable itself. The products of them, of even number of those, they are, if you wish. Even more, if you are not happy with such a definition, then you can just think about combinatorial formalism. That for some reason I want to study such quantities like ratios of functions like that. Okay, so comments on that. In this picture of flipping the sign of the interaction constant G across a chosen collection of paths, one can do a slightly more invariant thing. Instead of flipping, of changing the sign along this collection of paths, what one can do, one can say, okay, I'm given a collection of vertices, and what I consider a double cover of my graph. So one can consider a double cover of my graph. Okay, faces of G. Ramified over these. And to play the Ising model on the double cover of this graph, with the additional restriction that this is like a square root of z function, that each time I have plus on one of the sheets of this double cover, I assign minus to on the other sheet of the double cover. So that's a conceptual thing which is not that easy to grasp if you never heard about that. But yet again, so instead of, let's think about a function square root of z. Well, I can think about it as being a function in the full plane, but there is a story with a cut. So I must join 0 and infinity by a cut. And so there are two ways to handle that. Either I fix this cut, like I fix gamma v. And then I say that my function flip the sign when I go across the cut. Or a more invariant way, I can say, okay, I have a Riemann surface of this function, which is a double cover of the Riemann sphere. And then my function simply lives there, and this is a spinner on this double cover, meaning that it changes the sign between these sheets. I can do exactly the same thing with the Ising model. So I just fix ramification points. And what I do, I put pluses and minuses everywhere. But instead of saying that this interaction across the cut is counted with a different sign, I simply say I glue two sheets other way around. With the convention, let me write it, sigma mu sharp is minus sigma mu flat, where, okay, maybe mu prime, provided that mu and mu prime over the same face of mu. Mu star. Provided those are two faces which are above the same face of the original graph. This is a fair model. I can do exactly the same correspondence with such pictures. I can say that two spins, if they are not aligned on the same sheet, they contribute x. And the expansion would lead me exactly to this z v1 vn. Okay? And it has a byproduct. A byproduct is that when I think about these correlation functions, there is a non-trivial issue of signs. Because, okay, this variable, it depends on gamma v. And, okay, in particular, when there are, so the distribution of this, the law of this random variable does not, but when I introduce additional mu's, there is now a problem. When I move the cut, that's the same problem as with the function of square root of z. I ask you a question, what is the value of square root of z at a given point? Okay, there is no continuous canonical answer. It is on the double cover. And the byproduct is that, okay, these quantities, they are defined up to a sign. These quantities are defined up to a sign. And the sign, okay, one can track what happens when points float in the plane, which is similar to this product. What I should do, I should simply take the product of all v's, the product over all q's, vp minus uq 1/2. So it changes the sign each time when one of the sigmas winds around one of mu's. Okay? So in particular, okay, that's when all the disorders are far away from spins. This is okay, continuous, but when they are close to each other, there are some problems. Okay, Leo, I need 5 more minutes probably. I apologize for that. Is it fine? Okay. If somebody protests, well, just protest. Okay, and now there are 2 more key definitions. So the first definition is, okay, they both are quite formal, but there is a message behind them. So the first definition, let me write formally, given a corner C. So what is a corner? This is just a point, well, a corner of a face, right? Just a point in between of a vertex and the center of a face. So this is vertex, this is face. Let me write chi c to be just the product of mu and sigma, which doesn't make sense as a random variable, but okay, inside of this notation it makes sense. Just means that, okay, I have now an odd number of other disorders and m-1 spins. Okay? And now let me think about what is this, I mean, what is the issue of signs? What this issue of this product tells me. And this issue of the product of square roots tells me that when I think about correlations, when I think about the expectations of this kind, they're still defined up to a sign. But take a look, this is what is called Y or epsilon cross. So take a look on this weird construction of a graph on your problems. So now this is a double cover which branches everywhere. When I move around such a thing, it happens that v minus u makes the full turn in the complex plane, and because of that, this changes the sign. So this is not a function on a graph. This is a spinner by which I each time mean that it is defined on a double cover with the convention that the signs are just different on two different sheets. And the branching structure is like here. It branches everywhere. Just take a look on your thing. And there is a definition too. As I said, locally, the problem is just in the factor v minus u 1/2. This is exactly v minus u 1/2, which makes the full turn when I go around here, or just the full turn when I go around the vertex. So let me introduce another function, which is, okay, just the notation, eta c, which has the same branching structure. So the same branching structure, okay, it is convenient. I don't have time to argue about this now, but we'll see it next time, next lecture. It is convenient to choose such a notation first, instead of thinking about square root of v minus u, to think about the conjugate. And second, to introduce some fixed prefactor, which is of no relevance for now. Just you can think about constant 1 here. So this is a unimodular complex number which has exactly the same branching structure. And so what I can do, I can consider a product. So I can introduce a further notation. So I just think about these correlation functions with chi, and I correct them by multiplying by this eta. So what is the purpose? The purpose is that what I have now, it doesn't branch locally. So it is now a normal function on corners of my graph. So in the message, moral is that the expectations of psi c blah, 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 they do not branch locally. Okay, that's kind of a logical point to stop, but still after one more message. So, and the message is just in words. Now I can think about correlations of variables psi indexed by corners of my graph. Just psi c, psi d. A message. They coincide with the dimer correlation functions. So in the first half of the lecture, I told you that there is a formalism of dimers, which leads to correlation function, to this k minus 1 indexed by oriented edges, or c minus 1 indexed by corners of the graph. Message, correlations of psi are exactly the same thing as the correlation on the graph c hat, which is a combinatorial statement, not that hard to prove, but okay, some statement. What is more important is just to know that it holds. Okay, are there any questions? I apologize for being late. We will continue in half an hour anyway with this pain, I mean with exercises, just to understand what I was speaking about. Yeah, okay, still a quick question.
Sorry, so those sides corresponding to the quarters?
Right.
Are those random variables? They only have one?
Nope. They're not, I mean, this thing is not a random variable. Yet again, it contains one disorder which is not a random variable.
Okay, but if you normalize out by the...
But what I'm saying is that imagine that here there is a product of odd number of disorders and say odd number of spins, maybe including the boundary. Then this might be interpreted as a true random variable, if you wish. So yeah, somehow I try to balance. So in physics literature, you simply write a correlator and you don't care. I mean, is it a random variable or not? Who cares? It's just a function. Somehow I try to balance on the edge of probability. I try to say that, okay, nevertheless, each time there is an even number of disorders inside here, it might be thought of a random variable if you, purist, you want a true expectation.
общаться.
Ну, мы будем еще, я не знаю.
Можно?
Если ты можешь как-то быть модератором
Я
этого дела, мы были бы признательны, что